Did everybody find Doherty 2210 or whatever yesterday?
Yeah.
It's very challenging. I really hate Doherty. It's like disconnected, some parts of it. I should also like to remind you, please sign up for Piazza. This is like essential for following what's going on in the course. And I think maybe a third of you have signed up so far. So please check the course webpage. You can find the link and get signed up for Piazza. OK, so today will be our first kind of technical lecture. It's on two somewhat related topics, deductive systems and propositional logic. It's a bit definitional heavy, but what can I say? It's the first technical lecture. So let me tell you now why we're going to learn about these topics that are not obviously related to computation. Well, if you remember this person, David Hilbert, and you remember Tuesday's lecture, you'll recall that Anil told you that in the history of computation, it all started with the formal definition of what it means to compute something and what the formal definition of an algorithm was. And this was motivated by a problem proposed by Hilbert called Entscheidung's problem, which asked basically, given a logical formula, is there an algorithm that can determine whether or not it's true, or whether or not it's a valid formula, or whether or not it's provable? Okay, and in light of this, people decided to think about what the meaning of an algorithm is, and that led us to the theory of computation. But we'd like to think about this problem specifically, because if you take a look at it, one aspect of it is understanding what it means to determine the validity of a formula, or to prove a formula, or to deduce a formula. So because of this part, we're going to need to talk about this notion of deductive systems. And of course, the other part of this sentence talks about logical expressions. So we're going to have to talk about logic. Okay, so these are the two parts of this first lecture today. Okay, so let us start with deductive systems. So I'll explain what I mean by this with an example. Okay, so say you have $0 in your pocket and you walk up to an ATM, such as this one. It looks like the one in the third floor. Okay, and this is a bit of a strange ATM. It can dispense $2 bills and $5 bills, and any number of them, $2 bills or $5 bills. $2 bills really exist. You may see them from time to time. Yeah, unless this seemed like an early advertisement for PNC Bank, I chose them because some of their ATMs had this amazing property. I don't know if you've seen this one, where they can dispense multiples of $1, which is awesome because most ATMs will give you multiples of 20. You ask for $50 and they're like, I can't do it. But some of them, I don't know if the one in third floor can do it, can dispense even $1 bills. And whenever I see it like this person, I'm always like, yes, I'm taking out $64 today. So let's imagine that we have this semi-realistic ATM, which can give out $2 bills and $5 bills. And here's a little puzzle, the likes of which maybe you've seen before. Which different amounts could you possibly leave with? Okay. For example, you could leave with $7 if you got a $2 bill and a $5 bill. Okay, so do you want to think about it for a bit? Can you leave with 8? Yes? Who said yes? How? Yeah, you can get 4 $2 bills. What else is there? What can somebody suggest what numbers you can get? Yeah, I got a vote down here that probably not many people heard, so I'll take one more person and see if it matches. Anything above 5? This was actually slightly more accurate. You can also get 2 and 4. Yeah. Good. Wow, you guys are good. So yes, you can get any natural number except for 1 and 3. Now, I raised this example not so much because of its actual, arithmetic puzzle nature, but more because it's an example of a simple problem that can be modeled with what I'll call a deductive system. Okay, so this box kind of contains it as a deductive system. We have an initial object, which is the number 0. And we have two what I'll call deduction rules, which is that if x is deducible, or in this context, x is an amount that you can get, then you can also get x plus 2 by doing, adding a $2 bill. And also, if you can get some amount x, then you can also get x plus 5, by adding a $5 bill. Okay, so a deductive system is kind of like this. You have some initial objects and some deduction rules that tell you how you can generate new objects from ones you've already gotten. So this is exactly what I've just said. In general, it doesn't have to be numbers. We'll see some examples where it's not about numbers. But you have some initial objects, and this is the most important thing. A deduction rule tells you how you can take objects that you've already generated and generate new ones. Okay, and you can keep deducing, in general, more and more things. Let's do another example. I think it'll help clarify the situation. Here's an example involving parentheses, brackets. So I'll just describe it as a deductive system. So in this system, the objects won't be numbers. They'll be strings. And there'll be strings made up of two kinds of characters, this open parenthesis and close parenthesis. And we'll have one initial object, the string, open, close, this little pair of brackets. And there'll also be two deduction rules. And I'll give them names wrap. And that rule says if you've got a string S, you can stick an open and a closed on the outside. And concat, that stands for concatenate, which means to stick two strings together. And it says if you've deduced S and you've deduced T, then you're also allowed to deduce S stuck together with T. OK, so let me put that up here in a little box so that you remember it. And just so it's kind of clear, let me talk about an example. Suppose I ask you the following problem. Deduce this string. OK? Let's also, maybe you can all try it. Can you figure out how to do it? If you have a piece of paper in front of you, give it a try. I don't think there's a unique answer, but I think there's more or less only one way to do it. Maybe, have you figured it out? Put up your hand. Some people? Okay. How many steps did it take you? Yeah, I think you could do it 4. I'm getting some of these. Yeah, I think you can do it like the following. It's a little hard to read these annoying parentheses, right? But, well, you can start with the initial object. That's one thing. You can always deduce the initial objects. Those are allowed. And now I think I'm going to try to build up this piece in the middle. So I can apply the wrap rule to what I've already got and get this string. And now I'm in good shape because I have this piece and that piece. So I can apply this concatenation rule to combine these two strings that I've already deduced and get this string. And now I'm almost done. I just have to put the outside parentheses on this string. Okay, so this is how you would deduce this string. Okay, and you don't always have to apply the rules to objects you just deduced. You can always use any object that you've ever deduced so far. Okay, and that's the end of the proof. And in math, we put a little box usually at the end of the proof. In the olden days, they would write QED, which stands for some Latin thing. That's considered very pretentious now. At least I consider it very pretentious. We don't speak Latin anymore, so I highly advocate the box to finish your proofs. OK, any questions about this? No? OK, let's do one more example, just so it's all clear. Actually, wait, before I go to this example, we'll come back to this point later, but can somebody suggest what kinds of strings you can get from this deductive system? Yeah?
Any valid sequence of parentheses?
Yeah, the suggestion was any valid sequence of parentheses. What exactly do you mean valid, roughly?
Every open has a corresponding close.
Yeah, you would think everyone has the open has a corresponding close. They should be properly balanced. It's not super clear, but well, we'll talk about it later. That's in fact true. Anyway, we'll come back to that later. Let me give one more example. Both of those previous examples were kind of about modeling some situation you already have. The ATM example, we modeled it with the deductive system. Maybe that parenthesis example was about modeling matching parentheses. Again, we'll come back to that point. This is an example where we use a deductive system just to define an object. And it's a very important object in computer science, theoretical computer science, the binary tree. So probably you all know what a binary tree is, but let me give a definition using a deductive system. So I won't actually write it with the initial objects and the deduction rules, but you'll see that it's an example of a deductive system. So I start by saying this is a binary tree, one with one node, one vertex. And here are the sort of deduction rules by which I can generate new binary trees. Suppose you've already generated two trees, and I'll call them L and R. These are binary trees. Then these are also binary trees. You're also allowed to make bigger binary trees out of them, basically by one of these three methods. You can start with a new node and stick one binary tree you've generated on the left as a left child, or you can stick it on the right, or you can stick both of them in. So the node at the top can have a left child, which is a binary tree, and a right child, which is a binary tree. OK, and this is actually a good way to define what a binary tree is. Let's again see one more example of how this can define a binary tree. So as always, when you're doing these deductive systems, you have to start with the initial objects. That's the only thing that you have. So at the beginning, the only thing you know is a binary tree is a single vertex or node. And so we have to apply a rule. These subtrees that we're going to apply it to, L and R, just have to be this single node. So we'll, for example, apply the add both rule, and we get this as the result. So this is also a binary tree. OK, and now maybe we could apply the add left deduction to this binary tree. And we get this tree. And then maybe we could apply the add both deduction to, let's say, this tree and this tree. Actually, you have to decide whether this will be the left tree and this will be the right subtree, or vice versa. So let's say you choose this to be the right subtree and this to be the left subtree, and you get this tree. OK, so this is an example of deduction that sort of proves that this is a valid binary tree. Any questions? OK. While we have binary trees, maybe you've seen them before, but in any case, I'd like to remind you of some binary tree terminology, because they come up so often in computer science. These circles or nodes are called nodes or vertices. These lines are called edges. The one at the top is called the root node. And the other important concept are the leaf nodes. A node is a leaf if it has no children. OK, so this one has 4 leaves. This one is not a leaf because it has one child. OK, so this is a binary tree. It's usually drawn like this. It's also a bit weird because if you have a real tree, the root is at the bottom, right? And the leaves are at the top. Maybe unless you're in Australia. But somehow in computer science, it's always drawn like this, with the root at the top and the leaves at the bottom. Is anybody here from Australia? Oh, sorry if that's offensive. Cool. OK. Great. So that illustrates one good use of a deductive system, just to actually define objects. OK, so let's play a little bit more with deductive systems and see what kind of questions arise when you're talking about them. And we'll go back to this ATM deductive system, because it's kind of a very simple one that hopefully will be good for getting the point across. So just to remind you, here the initial object is the number 0. And we have 2 deduction rules, which you might call the +2 rule and the +5 rule. So here's like a very, very simple problem. Show that 4 is deducible. Let me not insult your intelligence by asking you to figure this out. Here's a solution to this problem. You can deduce 0, because it's the initial amount. And then you could do +2 to get 2. And you could do +2 to get 4. Okay, here's another one. 7 is deducible. Actually, I said this one verbally earlier. So here's a proof. You can deduce 0, and then 2, and then 7. Let me make it trickier. 17. Can you show that 17 is deducible? Actually, I guess if you were doing this efficiently, you could just, we did 7, and you could add 5 twice, right? But somehow that's not, when I was making these slides, that's not how I did it. Maybe I was having a bad day. This is how you can do it. And actually, this at least it illustrates a point, right? Which is that you can do things in more than one way. That's all right. I mean, there's not necessarily a unique deduction for each object. Anyway, here I did by going like 2, 4, 6, 8, 10, 12, and then I was like, oh, I'm going to need to get to the odds. 17. OK. So far, so good. And I also bring this up to illustrate a point that is worth remembering, which is that, let's say I give you a specific object and it's really deducible, like 17. Like I don't give you 3, but something that's really deducible, like 17. Basically, you can always, in principle, prove that it's deducible, show that it's deducible in like a brute force way. Like this is a valid proof, and it's kind of a brute force proof where you're just like, voila, I deduced it. OK, good. So let's try to increase the difficulty a little bit. Well, this is what we talked about before, right? When we all kind of decided, or many of us figured out, that you can deduce any number other than 1 or 3. So let's try to prove this. And let's make a simple but important observation, which is that actually now there's infinitely many objects that we all have to show are deducible. 0, 2, 4, 5, 6, 7, 8, etc. Okay, so whereas if it's just one object, like 17, you can just be like, here it is, there's the deduction. But of course, you can't simultaneously show infinitely many deductions. So you need to give a proof that's, a real mathematical proof written in English that explains why all of these deductions are possible. Okay, so instead of just explicitly giving one deduction, you'll prove that all of these deductions are possible. And really, it's a bit computer science-y, because what you really have to do for each possible number other than 1 or 3, you kind of have to give a recipe or an algorithm for how to deduce it in this deductive system. OK, so let's try it. Actually, does anybody have a suggestion? Yeah? OK, the suggestion was to split it into cases even versus odd. What are we going to do about the even numbers? Yeah, you can just keep adding 2 over and over to get all the even numbers, right? Again, there's actually multiple proofs, and this one of splitting into even odd cases is the one I also chose. But there's other ways to solve this problem. So anyway, let's say we did all the evens. How are we going to get the rest of them? Yeah, at the back?
Start at 5 and then add 2. So it's the same thing.
Yeah, that's right. Start at 5, and you can add 2, and that'll get you 5, 7, 9, etc. That's all the odds. Is that everything? Yeah, I guess that's everything, right? OK, so that's more or less how I wrote it. Actually, next year I'm going to change it. That's like, I think, even a little bit simpler than what I wrote. So I wrote it like this. And I really wrote it out formally, although this is not such a hard problem. Let's do a little lemma, which is like a part of a proof. And as suggested, show that if n is an even non-negative integer, then we can deduce it. Well, the proof is if n is even, we can write it as 2 times k for some natural number k. And then we can get n by applying the +2 rule k times in a row, starting from 0. Let me take a little digression now. If you were like super duper pedantic, or if somebody was super duper pedantic, maybe they might want you to prove this statement by induction. You can kind of see how you could prove it by induction, right? I mean, induction on k. It leads me to the question of, it's something that Anil brought up in the last lecture. When you're writing up solutions, like how much detail should you give? And this is a very hard question because, writing proofs is really like a sociological process. It's like you and the TA who's grading you coming to an agreement about whether or not you solved the problem. And you want to convince the TA that you solved it. And we don't exactly tell you the standards of like how much detail is enough, how much detail is too much. So you kind of have to get the feel for it. But a general rule is, at the beginning of the course, we want you to be really, kind of precise and fill in all the details and so forth. And as we, proceed through the course and get better at these things, it's a little bit more like, if something is obvious, it's OK to say that it's obvious. So here I think this is a good level. I think it's too much to ask you to prove this by induction. I mean, come on, this is a pretty reasonable proof, right? Maybe by the end of the course, you could even just say, it's clear we can get all the even numbers by applying the +2 rule a bunch of times. I think this is a good amount to write, for example. OK, where were we? We were showing that all the non-negative numbers other than 1 and 3 can be deduced. OK, so we got all the evens. So let's put that lemma in our pocket. And we just have to get all the odd numbers that are at least 5. So let's say n is such a number. It's odd and at least 5. Let m be n minus 5. Now, m is non-negative, since n is at least 5. And m is even because it's an odd number n minus another odd number 5. And odd minus odd is even. So by the lemma, we can deduce m. There's some sequence of deductions that gets us to m, which is n minus 5. And then we could do plus 5 at the end. OK, so this actually, as I said, maybe a little, I like maybe the earlier suggestion of starting with 5 and then just keep going up with +2s. I did it a little bit backwards here. OK. Any questions about this? Yeah.
You want to show that n equals 1 and 3 can't be deduced?
Ah, very good. You have exactly anticipated what is on the next slide. The question was, have we completely characterized the numbers deducible in this ATM deductive system? Well, not quite, right? We showed that everything other than 1 and 3 can be deduced. But to finish the job, really, we have to show that 1 and 3 cannot be deduced. This is also a little bit obvious, but let's do it. Because, I mean, in order to get a full characterization, to exactly kind of explain, that's what a characterization means, to explain in another way exactly the set of things that can be deduced. You know, we have to show that 1 and 3 cannot be deduced. This one's a little obvious, but it's the first technical class, so let's be pedantic and do it. Can somebody say why 1 and 3 are not deducible? Yeah.
To get an odd number, you need a +5, but once you do a +5, you're already past the number.
Yeah, the suggestion was to get an odd number, you'll need +5. But once you do +5, you're already at least 5, right? That's reasonable. There's several ways to write it. Let me show you in a second. But let me make this point, which is that this example is pretty easy. But in general, it can be quite tricky to show a certain object is not deducible, even if it's just one object, like 3. Because again, you have to show somehow infinitely many things. You have to show that in the case of 3, every possible deduction does not lead to 3. So let's spell it out, though. Actually, I'm not going to read this. You can maybe read it in the slides afterwards, but it's a different way than what was suggested. The way I said it was, let's first show that 1 is not deducible. It's not an initial object. So therefore, you would have to get it by a deduction rule. And if you got it by, let's say, the +5 deduction rule, then you must have come from -4. But all the deducible things are non-negative. I think that's obvious. Or you could have used the +2 rule, but then you would have had to come from -1, which is also negative. So that's impossible. So 1 is not deducible. To show that 3 is not deducible, again, it's not initial. So if you ended a deductive proof with 3, you would have either had to come from -2 by using +5. That's impossible. You can't get to -2. Or you would have had to come to 3 via the +2 rule from 1. But we showed that 1 is not deducible. OK, any questions? So sometimes these problems are not too complicated, but I wanted to use this example to just really illustrate how to take care with checking all the cases, what it means to prove that something is deducible, what it means to prove that something isn't deducible, etc. We'll talk a little bit more about deductive systems. The last thing we'll talk about, I'll base it on this other deductive system, the parenthesis deductive system. Let me remind you, this is the one where the objects are strings of open and closed parentheses. The initial object is just left-right parenthesis, the length 2. And there's the wrap rule where you put parentheses around something you already have. And the concatenation rule where you stick together two strings that you already have. So it was suggested earlier that the following is a characterization or another explanation for exactly the set of strings that you can deduce here. All the strings that are like balanced parentheses, like proper strings of balanced parentheses. I think you know what that means. So suppose I wanted to prove that. So there are two things I really need to prove in order to prove such a characterization. Can somebody suggest one of those things? Yes?
If the string parentheses is deductible, then it is balanced.
Yeah, if the string is deducible, then it is a balanced string. Yeah, that's one thing you need to prove. That's sometimes called, I don't know if I want to introduce this terminology now, but it's sometimes called soundness. It says for the idea that you have in mind, balanced parentheses, anything that you can deduce is really corresponds to that idea. It's a balanced string of parentheses. Okay, and what is the other thing I need to prove? Yeah?
It's not balanced, then it's not deducible.
If it's not balanced, then it's not deducible. That's true, but that's actually the same as the first thing. If it's not balanced, then it's not deducible. The contrapositive of that is that if it is deducible, then it's balanced. That's good, yeah. This is one, that's the way of thinking about it corresponding to what we did with the ATM. We're characterizing which ones are not deducible. Yeah, over there. Has the same number of open parentheses as closed parentheses. Anything that's deducible, you mean? Yeah, that's true. That's not quite the same as being a balanced string of parentheses, because you could have like right parenthesis followed by left parenthesis. That's a string that has the same number of open and closed, but it's not balanced. But that's part of what you'll have to prove. In the red?
All balanced parentheses are deducible.
Yeah, all strings of balanced parentheses can be deduced. Okay, so let me put them up here on the screen so that we can remember. We actually said the number 2 first, that any string that can be deduced really is a balanced string of balanced parentheses. And how would you prove that? This you would prove by induction, by structural induction. And if you kind of don't remember about that so well, we'll talk about it, I guess, in the recitation tomorrow. But basically, to show that anything that you can deduce is a string of balanced parentheses, it's going to be an induction, right? You'll say, well, the initial object, which you can deduce, is just left, right. That's balanced. And you want to show that the deduction rules preserve balancedness, right? That if you wrap a balanced string, it's still balanced. And if you concatenate two balanced strings, they're still balanced. And the other thing we have to prove is sort of the converse, not the contrapositive, but the converse, that every string of balanced parentheses can be deduced. This is a little bit like the showing that you can get every number other than 1 or 3. And again, you have to kind of give a recipe or an algorithm that sort of says for each string of matching parentheses, of balanced parentheses, there is some way to get it by starting from the initial object and putting together the two rules. Okay. Any questions? Yeah.
You have to be a bit careful with the induction for the first part to make sure that your induction step actually covers all strings and balanced parentheses.
You're talking about this one?
Yeah.
Yeah, okay. It's not immediately clear that you would improve this one by induction. The overall idea is, if I gave you a specific string like we did before with 8 characters, and said show that this is deducible, you would say, well, wrap this, concat that until you get to the end. Here it's a bit trickier. You have to say if somebody gives me any old string that's balanced parentheses, you have to explain how to get a sequence of deduction rules that gets to that string. In fact, the TAs will exactly discuss this problem in the recitation, and you will actually eventually need induction for it. But indeed, you have to be careful that it works for every string of balanced parentheses. Any more questions? Actually, I have a question. What does it mean exactly, balanced parentheses? I kept saying like, oh yeah, you know what balanced parentheses means, right? Okay, so what does it mean? What does it mean? Pardon me? They're well nested? Oh, that's kind of like saying that, they're validly, I mean, it's true, but what does that mean, I guess I would ask. Do you have a suggestion?
If you go through the string, you have more closed parentheses than open parentheses, and like before each revision.
Yeah, that's almost exactly right. The suggestion was, if you take the string and you go through it from left to right, you always have more open parentheses, or at least as many open parentheses as closed parentheses. And there's one more aspect to it. Somebody here want to say? Maybe you?
They're also the same number of right as left.
Yeah, there also has to be the same number as right as left. So not only as you're going along, you have to sort of always have more opens than closes. You also have to end with them exactly, the same number of open and closed. That's true. Actually, that's a little bit complicated though, right? I mean, to really explain exactly what is balanced parentheses, it's a little bit tricky. And in fact, you might actually just say, you know what? Maybe I just prefer to make this the definition of balanced parentheses. And then you would show that that property holds. Anything that you can generate here has this, if you parse it left to right, there are at least as many opens as closed, and it ends with equally many. So you really have two choices here. And sometimes, eventually it's kind of cleaner to define things by deductive systems. But I guess maybe in the end, for this case, it's a bit more natural to make this sort of complicated, but I guess ultimately intuitive definition of what it means to have balanced parentheses, and then show that that's the characterization of this system. Anyway, it's good to have two equivalent definitions of the same concept. Okay, that's all I want to say for now about deductive systems. Any questions? Okay. So, next part of the lecture is about propositional formulas and propositional logic and also circuits. Now, I guess based on the prerequisites, all for this course, everybody has seen some propositional logic before. I'll remind you of some things, but I guess I'll go through it a little bit quickly. So, propositional logic, on one hand, is invented by philosophers really as a model for some kinds of mathematical reasoning. So sort of lofty definition. Another way to say it is, that stuff with like the formulas that look like this with the variables and the ands and the ors and then the negations and truth tables and that kind of stuff. So let me remind you about this. Let me also just say that when we use this adjective propositional logic, it's just a weird word that means we're talking about the logic where it doesn't have quantifiers. It does not have for all, and it doesn't have exists. Just the ands and ors and implies and stuff. The extension, when you add on for all and exist, that is called first order logic, and we'll also talk about that, but in the next lecture. Okay, so propositional logic has a couple of ingredients. The first ingredient is propositional variables. Okay, and we usually write those as letters like P or W or X1, X2, X3 if we're feeling mathematical. And they stand for basic statements that can be either true or false. For example, in like the logic textbooks, they're always about like English language concepts. Like P stands for I'm playing tennis, and W stands for I'm watching tennis. R stands for I'm reading about tennis. I guess the Australian Open is coming up soon, so I had tennis on my mind. Computer science, when things get a little bit more like logic-y and about bits, you might have a variable that stands for just an input bit is 1. Okay, and this is where you're kind of on the more computer science side of things. We'll probably mostly stick with the real world for illustrative purposes. Okay, so that's ingredient 1, variables. The other ingredient is connectives, which are like these operators, well, there they are. We have 5 of them. Not, and, or, implies, and this is if and only if. Okay, and I'll remind you later what exactly they mean, but hopefully you remember at least, not, and or, and maybe also implies. That's kind of important. Okay, and when you combine these connectives with the variables, you get formulas. Okay, so you get stuff like this. This is a compound sentence or a formula. If you remember the tennis interpretation, can anybody say what this means? Like in words?
Not playing tennis means you're watching tennis.
Yep.
Not watching tennis means you're
Reading about it. Yeah, so okay. It's just a funny example if you really love tennis, and this is how you would formalize this sentence. Okay, so actually this step, going from like an English sentence to like a formula, we're not going to be like that interested in this step because it kind of depends what like English words mean and stuff. But this is how it's usually motivated in logic, if you wanted to reason about your tennis habits. See, there's another connection between sports and computer science. Okay, so if you look back at the previous slide, I did something that was like a little bit, funny. I was like, you got your variables, you got your connectives, stick them together, formulas. But that's not very rigorous. Suppose you wanted to formally define what is a formula, a valid formula. How might you do it? Yes, thank you. You could use a deductive system, and that's a nice way to define them. So a well-formed formula, given some variables, x1 through xn, and usually when you're working in generality in logic, it's best to call your variables x1 through xn, because you don't really know how many there could be, and you don't want to run out of letters. It's any string, so formula is a string, that you can deduce in the following deductive system. The initial objects are just single variables. A single variable counts as a formula. And then the deduction rules are that if you so far built up a formula A, then if you stick the not sign in front, that's also a formula. And if you've built up two formulas A and B, you can combine them with these other four connectives, any of them. These are binary connectives. They take two subformulas like this. And we put parentheses in just so that it's unambiguous. Okay, so I might ask you to, like on a quiz or something, to show that this is a formula, the one that we saw, and it's because, well, you start, P is a variable, so it's a formula. Then you can deduce not P using this rule. W is a formula because it's a variable. You can deduce not P implies W by using this rule, etc. Great. Now actually, there's another equivalent viewpoint on formulas, which is also good to know, and it can help when you're reasoning about formulas to have both ideas in mind. A totally equivalent definition is that a formula is a binary tree, like we defined earlier, where the nodes have labels on them. Any node that has two children should be labeled by one of the binary connectives, and or implies, or if and only if, like these ones. Any node that has one child should be labeled by not. In any leaf, any vertex that has 0 children should be labeled by a variable. Okay, and then you kind of see how this formula corresponds to this tree, for example, right? Overall, this formula is a big and what are the pieces in the and? Well, the left piece is overall implies. And what are the pieces of the implies? Well, the right-hand part is just W, which is a variable. The left-hand part is overall a not, so we have not P. Okay, so any binary tree with this kind of labels corresponds to a formula and vice versa. Any questions about that? Okay, good. So we know what a formula is. So now let's talk about the next component, which is truth. So if you go back to these old-fashioned kind of statements about the real world, maybe I might ask you to model this English sentence by a formula. If potassium is observed, then so are carbon and hydrogen. So maybe you would write that like this, where K stands for potassium being observed and C and H are carbon and hydrogen. So that's a nice little formula. Okay, so is this statement true? Well, it's a trick question. This question does not make sense. A formula is not true or false. I mean, a formula is just a string. But whether or not it's true, whether or not a formula is true, depends on whether the variables are true or false. Okay? So it depends on like the state of the world. For example, now I'll ask you a question that makes sense. If k is true and c is true and h is false, then we could say, is the formula true or false? I'm getting a lot of votes for false. Let's see. Well, c and h will be false because true and false is false. And then you have true implies false. That's false. So yeah, it's false. I'll remind you later how this exactly works. But again, you've probably seen it before. What if k is false and c is false and h is true? Oh, you guys are good. Well done in the prereqs. Yeah, it's true because this piece, c and h, is false. K is false, and then false implies false is, weirdly true. Like, you have not falsified the statement because potassium was not observed. So, yeah. Okay, so just to illustrate that, formula is true or false depends on whether or not the variables are set to true or false.
Can you say a formula is true if it's like a tautology?
We will get to exactly this point. It's kind of, some formulas are always true for all settings of the variables. Those are called tautologies, and we'll get to them. But I prefer to say that, a formula by itself is not inherently true or false. But it's a good point. Okay, so let's make this clear with some definitions. Truth assignment. I did not mean to have an irregular sigma character here. This should be a V. PowerPoint has screwed me once again. I'll fix that. I do like PowerPoint, though. Okay, a truth assignment V, not variant sigma, is a setting of true or false for each variable. So given a formula S, we can define its truth value, which I'll write as V of S, by structural induction. Remember, a formula, we kind of defined it by a deductive system, and kind of whenever you're proving something about something defined in a deductive system, you're basically always using structural induction. So I won't actually write an induction here. I'll just kind of sketch it to you, because it's pretty clear, I think. The base case for formulas is that the formula S is a variable x. And if it's just a variable x, then the truth value of the formula is just the truth value of the variable. Okay, the truth assignment gives truth values to the variables. And in the induction step, S would be defined by a connective, one of the 5 possibilities applied to some subformulas. And then we use this like well-known table, right? Like for or, if false or false is false, and false or true is true, everything else is true. Okay? Any questions? All right. You can also look at this from the binary tree perspective, and that's quite nice too. So remember we had this tennis formula, and this was the tree corresponding to it. And you want to decide how a particular truth assignment, like P gets true, W gets false, R gets true, how it gives a truth value to the whole formula. Well, you kind of like plug it into the leaves and filter it up, right? So we plug in the truth assignment at the variables, which are at the leaves, and then we sort of filter things up. So this is negation of true, that's false. And this is negation of false, that's true. And then we have false implies false is true, true implies true is true. Okay, and we get up to the root, and the root has the truth value of the whole formula. Okay, so in this case, it follows that under this truth assignment, the whole formula is true. Apparently, it's possible that I'm both playing tennis and reading about tennis simultaneously. Okay, so now we know what it means for a formula to be made true or false by a truth assignment. Now I have to give you a slide with multiple definitions of terminology on it. Sorry about that, but they're important. They're easy. I mean, it's kind of clear from the name. So we say that a truth assignment V satisfies a formula S if it makes it true. Okay, satisfies means makes it true. We say that S is satisfiable if there exists a truth assignment making it true. S is unsatisfiable. It's kind of the opposite if there's no truth assignment that makes it true, or every truth assignment makes it false. And the last one is the one that was mentioned earlier. In a way, it's also kind of the opposite of unsatisfiable, but a different kind of opposite. S is a tautology if it's true for every truth assignment. Okay, this is maybe the one that's not so obvious from the name if you don't remember what a tautology is. It's a statement that's like automatically true no matter what the truth assignment is. Yeah?
Isn't this kind of using the quantifiers you said you wouldn't be using?
The question is, isn't this kind of like using the quantifiers like for all and exist that we, I said was not in propositional logic? This actually gets at a very good point. So when I'll talk about this more in the next class, but when we do math, we use like all the good old human math. We say sentences like, for all this, this happens, there exists X such that this happens. And then sometimes the math that we're doing is logic, which is this like funny game that involves like strings and formulas and stuff, which actually, we're playing this game because we think it models some aspects of mathematical reasoning, but there's a difference between like the logic that we're playing with and like the good old normal math that we're talking about when we're talking about this logic. So yeah, I mean, here I'm making a definition in English language. I say that S is satisfiable if there exists a truth assignment making it true. But I'm not actually using the exist symbol. I'm not trying to mathematically model that yet. But this will actually come up with for us in the next couple of lectures, sort of the distinction between the normal math that we use when we're writing proofs and like this particular part of math called logic, which weirdly enough is about modeling how we do math. Okay, so let's do some examples. Every formula is either unsatisfiable or satisfiable. And some satisfiable formulas are also tautologies. Okay, so this is a partition, unsatisfiable is satisfiable. And tautology is like a particular case of satisfiable. So if I said, potassium is observed and potassium is not observed, that's like K and not K. Where would that fit? That's unsatisfiable. It doesn't matter if K is true or false. This is definitely going to be false. This is the one that we saw before. K implies C and H. We saw that there was a truth assignment that made it true, so it's satisfiable. There's also one that made it false. So it's not a tautology. And here's an example of a tautology. If hydrogen is observed, then hydrogen is observed. Sounds pretty tautological. As a formula, it's H implies H. And you can see that for all possible truth assignments, namely H is true or H is false, the whole formula is true. So that's a tautology. So to summarize, tautologies are sentences that are sort of automatically true just for logical reasons alone. They're always true. Unsatisfiable means it's automatically false just for logical reasons alone. And things that are satisfiable but not tautologies, could be true and could be false. So their truth value depends on the state of the world or what the truth assignment really is. So let me give you an example of how to show that something, how to analyze the satisfiability of a sentence. So here's a funny looking formula with 3 variables. And the simplest way to reason about it is with the truth table. So a truth table has columns for each of the variables, x, y, z, and it has rows for all the truth assignments, the settings to those variables. So there's going to be 8 here. And then you also have a column for the formula that you care about. Sometimes it's also good to put in columns for the subformulas if you want to work it out. So then you can fill it in. If x, y, and z are all false, what does S become? Yeah, it becomes true because you have this is going to be false implies true, which is false. And this is going to be false implies false, which is true.
Wait, false implies true is true.
False implies true is true. Man, I fell into the classic error. Good. Or was I testing you? Or was it just, yeah. There's a lot of symbols up here. Good. So it's true if you work it out. Yeah. Good. So they're both true. Okay, and so what can we immediately conclude about S? it's satisfiable, because there's at least one thing that makes it true. Now, you could work out all the other rows in this table, and I did. Believe it or not, I think I did it correctly. And in fact, actually for all the other 7 ones, if you plug it all in, you get true. Like the last one, I think I can do this. You have true implies true, and that's equivalent to true implies true. So it's true. So that means that this sentence is actually a tautology. So this sentence is always true. This formula is always true, regardless of whether x, y, and z are true or not. You could try to think about maybe what the meaning is and why that's the case. Okay, so we just talked about how you can decide if a sentence, a formula is satisfiable or a tautology. And you can do it by the truth table method. That's the simplest method. And the good thing is that it always works. I mean, you just fill out the truth table, check what all the truth values are for the formula, you're done. Any downsides to this method? Yes, it's tedious. Not just tedious, but also, well, it takes a long time, right? If you have a sentence, if you have a formula with n variables, how many rows are in the truth table? 2 to the n, yeah. So it's going to take you, or your computer program, at least 2 to the n steps for sure to fill it in. There's 2 to the n things to fill in if you want to fill in a truth table. That's a very long time. I mean, if n is even something small like 42, that's like 4 trillion, which is a pretty big table. Actually, as an aside, it's a belief among most computer scientists, but possibly not Anil, that there is actually no efficient algorithm that can decide if a given formula as input is a tautology or if it's satisfiable kind of efficiently, let's say in polynomial time like n time or n squared time or n cubed time. Later we'll exactly define what this means, but let's say just efficiently right now. That's a very famous conjecture. It's called exactly the P does not equal NP conjecture that Anil mentioned last time. One of these $1 million problems from the Clay Foundation. It's probably the biggest open problem in computer science, one of the biggest open problems in all of mathematics. And there it is. I just told it to you. Checking whether a formula is, let's say, satisfiable cannot be done with a polynomial time algorithm. In fact, actually, among the believers here, most of them also believe that you can't even do it in 1.99 to the n time. So anything even a little bit faster than 2 to the n time. So not only not polynomial time, but not even anything fundamentally less than 2 to the n time. That even stronger conjecture is called exponential time hypothesis. And we may hear about it later in this course, or maybe not. This is definitely the more famous version of it. Another open problem about truth tables is who invented them. This is a historiological problem. And I was interested in this when I was preparing these slides because I think if you go to Wikipedia, it says that Wittgenstein invented them. And at first I was like, come on, no way, right? This is like a computer science concept. This guy is famous for being a philosopher, so did he really invent it? He scooped us? Actually, maybe it's slightly plausible because he used to be a mathematician before becoming a philosopher. He was a student of Russell, who some people also claim invented the truth table. But there are many other claims, like Post. He's a very overlooked guy in the history of computation. He kind of also invented a notion of algorithms besides that of Turing. He's like a math teacher in New York. Some people claim this American guy, Peirce, invented them. But you shouldn't forget Poland. Some people say that Łukasiewicz invented them. Jevons, I read somewhere. Jevons' student, Christina Ladd Franklin, I've read somewhere. So this is a challenging open problem, which may appear on homework too. Let me mention one more concept here, that of logical equivalence. This is a pretty easy concept. Sorry, though, for the lot of definitions. Oh, busted again. -1 to me. Two formulas R and S are said to be equivalent. And we write R is equivalent to S with these 3 lines. This should be a V again, sorry. If they have the same truth value for every truth assignment. Okay, so they're different formulas, but if you do the truth tables, they're exactly the same. So really, they represent the same logical concept, just expressed in different ways. So let me give you some examples of this. This one you might know, right? Not of x and y is the same as not x or not y. That's called one of De Morgan's laws. It says if they're not both true, then at least one of them is false. Okay, so these are equivalent. You could do it by making a little truth table with 4 rows and 2 variables. In fact, if A is any formula at all, not just a variable, then the same rule applies. The other converse version is that not of A or B is the same as not A and not B. And these two things are called De Morgan's laws. They let you move nots to the inside if you have A and B, or not A or B. There's lots of other ones. I mean, if you don't like this, implies A implies B is the same as not A or B. If you don't like this if and only if, A if and only if B, it's the same as A implies B and B implies A. You know, double negation is the same as the original formula. This is an important one. A or B is the same as B or A. That's called commutativity of or. And this one says that with ors, it doesn't matter where you put the parentheses. What's this one called? Again, good with the prerequisites. This is associativity. And this is nice because it means if you have like A or B or C, then you can just, this is technically not formally allowed, but sometimes we'll allow it, you know. We'll get a little bit relaxed. It doesn't matter where you put the parentheses or what order. If you have a big or, you can just write, you know, A or B or C. Similarly for and has all the same properties. You know, there's, you know, many, many more. A or A is equivalent to A, etc. So, you know, before we talked about how to show something as a tautology, one way you can do it is write down a giant truth table and check if it's always true. But if I ask you to prove that something is a tautology on a homework problem, you don't necessarily have to do it this way. Sometimes, you know, if you're lucky or you're clever, you might be able to figure out a different way to prove it's a tautology, maybe by using equivalences. Let me show you an example. So suppose I have this formula, x implies y and x implies y. Well, overall it's an implication, right? This piece implies y. And one of our equivalences was that A implies B is the same as not A or B. So we could use that here and say that this formula is equivalent to this formula, i.e. they have the same truth table. And now let's see, we have, we could use De Morgan's laws on the inside here. We have the negation of an and, so we can push the negation to the inside and change it to an or. And now we have a big or of 3 things. We could use the associativity equivalence to switch the parentheses around. And now we could say this is further equivalent. X implies y. We could use this rule again. It's the same as not x or y. So this formula is still equivalent to that one. They have the same truth tables. And now you could take a look at this one and say, actually, if you look at it, it's negation of s or s, where s is this subformula. And this thing you could, you know, I think fairly say is obviously a tautology, right? I mean, s is either true or it's false. So whatever that is, whatever case it is, you know, one of them is true. So not s or s is a tautology. Okay, so this formula is a tautology. Its truth table is all truths. And it's equivalent to this one. So this one has all truths in its truth table. So it's also a tautology. So this is an example of how you might prove something is a tautology without using the truth table method. Yeah?
Do there exist efficient ways to determine if 2 formulas are equivalent? Pretty much the same problem as the...
That's a good question. It's pretty much the same problem as determining if a formula is satisfiable or not. In fact, you can think about why that's the case.
You could just set it to true or false, and then if you determine they're equivalent.
Yeah. If I want to know if a formula is, let's say, a tautology, I could write down that formula if and only if x or not x, some other tautology. And so then they'd be equivalent if and only if The first guy was a tautology. That would also make a good homework problem. I'll save that for next year. Thank you. Okay, one more definition, I think, before we get on to another section about circuits. That's logical entailment. So we've been talking about a lot about whether a sentence S is a tautology. That's kind of an interesting question to ask, but actually in normal uses of logic, it's not the normal question you ask. You usually are more interested in questions like this. Suppose I have some formulas, A1 through AM, maybe called axioms, that I assume are true. Does that imply that S is also true? Okay, somehow, is S a logical consequence of these formulas? I'm not asking if S is always true. I'm asking if it sort of follows from these formulas. If it's true whenever the axioms are true. Okay? So here's the definition that encapsulates that. We say that formulas A1 through AM entail formula S, and you have to use this symbol. Good thing we're not using LaTeX this year, because you'd have to search out what this symbol is. We say that A1 through AM entail S if every truth assignment, should have just changed them all to sigmas. If every truth assignment which makes A1, A2 up to AM true also makes S true. In other words, S is like a logical consequence of A1 through AM. Does this concept make sense? I'll illustrate it now with some examples. Okay, some entailment examples. So X and Y together entail, or you can deduce from them, X and Y. Okay? X and Y is not a tautology. It's not always true. But if you assume X and Y are true, then X and Y is also true. Or generally, A and B together entail A and B. If you assume A is true, then any statement like A or B is also going to be true, regardless of whether B is true or not. Okay, this is a very famous entailment example. In the olden days, they called it modus ponens. I don't know what that means. If A is true and A implies B is true, then B is true. Okay? In other words, B is a logical consequence of A, and the implication A implies B. These are examples of kind of the rules you actually use in everyday life when you're proving mathematical theorems. If A implies B and B implies C, you can deduce that A implies C. This is a famous one. You have to think about it a little bit. This is kind of the rule of case analysis. If you have A or X, you have B or not X, then that entails A or B. You have to think about it a bit why that one is true. Basically, if X is false, then A would have to be true. If X is true, then B would have to be true. X is either true or false, so at least one of A or B has to be true. And you might think about that one a little bit, etc. The good thing about entailment is it doesn't really introduce a new technical concept. Because what does it mean for A1 through AM to entail S? It just, by definition, means whenever all the A's are true, S is also true. It's the same as saying that this statement is true. The and of all the axioms implies S is a tautology. Okay, any questions about that? So for example, if you want to give something complicated situation, you want to check if some formulas entail another formula, it's the same as checking this thing being a tautology. Okay, so the last 15 minutes or so, we're going to move a little bit from logic to computation. After all, this course is called Great Theoretical Ideas in Computer Science, so we should talk a little bit about computer science as well. Usually in logic, you write false and true, but when you move to computation, usually you write 0 and 1. Okay, these are the same things. You can write whichever one you please. They're identical. I'm going to start writing 0 and 1 instead of true and false. These are bits. So one thing that we saw with the formula is that every formula has a truth table. For example, if you have this formula with 3 variables, it has this truth table. And I wrote it with zeros and ones. It's kind of nice actually to write with zeros and ones, right? Because then these rows are all the, I don't know if you can read that, these are all the length n binary strings. Okay, you can just order them by the binary expansion of 0 through 7 in this case. So it's the nice way to organize your truth table. A truth table also represents a Boolean function. So what is a Boolean function? It's just a mapping from bit strings to bits. Kind of like you have an input string and an output bit. Okay, so in function kind of notation, this 0, 1 to the n is the notation for all strings of length n. In this case, n is 3, using 0 and 1. And a truth table really tells you like a mapping from all of these, each of these strings to a single bit. By the way, a Boolean function, let's say a 3-bit Boolean function, you can specify it by a truth table like this. You can just say for each strings exactly each choice x, y, and z exactly what f, x, y, z is. That can be a little bit big if the number of variables is big. You can also specify it by words. For example, you could say, well, f, x, y, z is the function which is 1 if and only if at least 2 of the input bits are 1. That's a way in words to express this function, or this truth table. Here's a little question for you. Say I have n variables. How many different Boolean functions, or how many different truth tables are there? Somebody want to say it in a loud voice? I was trying to trick you. It's actually not 2 to the n. 2 to the 2 to the n. That's right. That's very large. Why is that? Well, let me ask. Why is that? Yeah? Or?
Because you could also represent the function as a bit string of length 2 to the n, and then there are 2 to the n.
Yeah, I see what you're saying. So the truth table itself has 2 to the n rows if they're n variables. And so really this column, as was suggested, is like itself a string of length 2 to the n. So in other words, there's 2 choices for each of its bits. So it's 2 to the 2 to the n. Okay, so we know that every propositional formula on n variables, it has a truth table. And you can kind of think from a computation point of view as this formula kind of computes a Boolean function or computes a truth table. One of these 2 to the 2 to the n truth tables. Okay, so actually we're seeing, in some sense here, a little model of computation. It takes in input bits, and a formula kind of spits out one output bit. Okay, just like Anil was talking about, there are many different things that you can think of as doing computation. Let's ask the converse now. Is it true that every Boolean function or truth table has a formula that computes it? We got one vote for no. Should we do a vote? Who would vote for no? Who would vote for yes? Okay, there's a lot of abstainers. But we'll go with majority, which was yes. Let's see why that's true. I'm going to show you by example that whatever truth table you write, there's some Boolean formula which has that truth table. Or every Boolean function can be computed by some formula. So let's start slow. Let's say there's 4 variables, so I'm going to consider truth tables that look like this. Here's one such function. It's mostly zeros, but it would be 1 if all the input bits are 1. Does anybody know a formula that computes this? Yeah?
X1 and X2 and X3.
Yes, the and of all 4 variables. And here I'm doing this informal thing. We know that it doesn't matter where you put the parentheses, so we can just write a big and like this. How about this one? Can anybody do this one with a formula?
No, there's
Okay, she started talking, sorry.
not X1 or X2 or parentheses.
Not quite. It was a good start. Not x1. Now I'll come to you.
Not X1 and not X2 and not X3 and not X4.
Yeah, this one is true if and only if all of them are false. So it's not x1 and not x2 and not x3 and not x4.
Wait, couldn't you just not be or?
Yeah, that's
for De Morgan's, not X.
Oh, sorry. I take it back. I didn't hear the parentheses. She said something, yeah, maybe she's like not of. Wait a minute. No, that's not right though, right? If you do the not of this one, you'll get this thing that's. Oh, with the ors. Man. Okay. Yes. Good. Sorry. There are many different formulas that compute the same Boolean function. Thank you. Yeah. Not only do you have to answer the question correctly, you have to psychically know what I'm thinking is the correct answer to the question. I'll try to listen better. Okay. So good. How about this one? Shall I give it to you? Or do you want to let somebody else try? Okay. Anybody else want to do this one? How about your neighbor? Were you also putting up your hand?
X1 and not X2 and X3 and not X4.
Yeah. You can see you kind of, this has 1, 1. You kind of pick it out by saying X1 and not X2 and X3 and not X4. Okay, or here's another example. If you just have all zeros, but this one is a 1. This could be not X1 and X2 and X3 and X4. Okay, so I think kind of maybe you see that you could similarly do any truth table if it had exactly 1, 1. You know, you just kind of see where the what row has the 1, and you kind of do a big and that it sort of exactly picks that one out. What if there's 2 1s in the truth table? Hold on a sec. So like here's a truth table with 2 1s. What could you do for this one? Yeah, you can get the formula for that's 1 on this string and the formula that's 1 on this string and OR them together. Like this. Okay? What if there's 3 1s? I mean, we just took care of a lot of cases. I hope this is clear, right? I mean, if you have 3 1s, this one, and this one, you make a big AND that's true for this string, a big AND that's true for this string, a big AND that's true for this string, and you can OR them all together. Okay, so we've just kind of done now a proof by example for the following result. By the way, you may not do proof by example on your homework, but I have the privilege of getting to do it in the lectures. Every Boolean function or truth table over n variables can be computed by some formula. And actually, as a little bonus, you see we only used and, or, and not. So if you want, you only have to use and, or, and not. Actually, there's another good reason not to use proof by example, even though I did it, because if you don't do it properly, you may make a mistake. Actually, I have not really proven it. I missed the case. Somebody think of it.
No
Okay.
ones.
Yes, I didn't really illustrate what if you have a truth table with no 1s in it. So do not do proof by example. But that one's also okay, right? The Boolean function, which is always 0, you could use, I don't know, x1 and not x1. Okay, that's any unsatisfiable formula. Okay, any questions about this? So that's good to know. I mean, every Boolean function can be computed by some formula. That means that, in particular, we can deduce that every Boolean function is equivalent to a Boolean, every formula is equivalent to another formula that uses only ands, ors, and nots. So you can take that formula, write its truth table, do this procedure to get another formula with just ands, ors, and nots that has the same truth table. Okay, one last topic, which is that of circuits. So since we already talked a little bit about computing and computing Boolean functions, if you've seen circuits before, or you're an electrical engineer, you might be thinking about this concept. So I want to talk a little bit now about circuits, which are very similar to formulas, but there's some subtle difference. And maybe with 6 minutes left in the class, it's not the best time to introduce subtle differences, but this is where it fit in the lecture. So this is a formula. And if I said, why is it a formula? You'd say, okay, if you really want, I can deduce it. X is a variable, y is a variable. Then I can make x and y. Then I can make y or z by doing or to these two. Then I could do an and to get them together. And then I need to get x and y negated. That's convenient because I already have x and y here, so I can just apply the not rule. Okay, and I'll OR them all together. There's your proof. This is a formula. Okay? So far, so normal. There's also the tree version, right? I mean, I told you that every formula is also equivalent to a tree. Here's the tree for this guy. You know, overall, it's a big OR. The left piece is a big AND. The right piece is a negation. It's a negation of x and y, etc. Okay? Now, actually, if you look at this tree, and you look at this deduction, the tree represents the formula, that's true, but it doesn't really represent the deduction. Like, I would not say this tree is a picture of the deduction we just did. What do I mean by that? Well, suppose I wanted to sort of draw a picture illustrating this deduction of the formula. This is how I would do it. I would say, well, we got x, y, and z. And then we first built x and y, like this. And then we were like, well, we're going to need y or z. So let's OR them together. Actually, already something different has happened here that didn't happen before. I have 2 lines coming out of the y. Well, anyway, but then we said, let's AND them together. You might draw that like this. And then we're going to need the OR it with negation of x and y. And in the deduction, we said, hey, we did x and y like a few steps ago. It's right here. This is x and y, so we can just negate it. Okay, and then we OR these things together. And that's how we deduced this formula. Does that make sense? You see, it's not quite the same as this formula. So can somebody say what's sort of different about this? By the way, is a picture of a circuit. Okay, you've probably seen circuits before. They look like this. By the way, the terminology is that in circuits, these are called gates, the vertices. And the lines are called wires because, you know, I guess these were actually invented by electrical engineers who implemented them with actual wires in the olden days with like voltages on them to represent true and false. And the gate was like a little physical object that had wires coming in and wires going out. These are the inputs, and this is called the output wire. So that's the terminology. Can somebody sort of say what the main difference between this circuit is and the formula tree? Yeah?
I mean, you have nodes with more than one parent. It's not a tree, it's more of a graph.
Yeah. This is not a tree, for example, because some nodes have more than one output. In other words, another way to say it, well, let me just say, in a circuit, there's a concept of a gate having fan in, which is the wires coming in, or the number of wires coming in, and fan out, which is the number of wires going out. And if you think about that concept with the formula, in a tree, everybody has one parent, so that's sort of everybody has one fan out. But in circuits, you're allowed to reuse pieces. We use this AND kind of twice. Okay, so that's the difference between a formula and a circuit. So in particular circuits, the nodes can be used more than once. They have fan out bigger than one. A formula is a tree. It has fan out. All the nodes have fan out 1. Another way to say it is that the circuits can reuse pieces or subformulas they've already computed, but formulas can't. They kind of have to rebuild each piece every time they want to use it. You can see an example of that here. We have x and y. We kind of needed to build it twice. So because of that, circuits can kind of be more efficient. And from a deduction viewpoint, this is a bit subtle, but it's a nice thing to think about. If you deduce a formula, the formula is the last line. It's what you deduced. And the circuit depicts the actual deduction itself. Okay, let me say one more thing. I have one last slide. about circuits. It kind of illustrates an important mystery of theoretical computer science, kind of similar to the P versus NP problem and related to some things that Anil talked about. So circuits are kind of like a way to compute things. They're sort of like a programming language, especially if you think about them in the deduction format. You might ask how efficient they can be. Let's think about all the truth tables that have 42 variables. It's not too hard to show, and we're going to show this eventually, or we'll see why later, that there's some 42 variable truth table such that if you want to build a circuit that computes it, you need at least 100 billion gates. That's pretty big. Even though it has only 42 variables, you can have a really complicated truth table. The smallest circuit building it, implementing it, uses at least 100 billion gates. There's a funny thing, though. We only know that it exists. We don't actually know an example truth table with that property. If somebody actually had to come along and say, check out this definite explicit truth table that I explicitly described, I can prove that if you want to build a circuit for it, it needs at least this many gates. The best thing we know is 123. We do know one function with 42 variables that definitely needs at least 123 gates. And we can explicitly say what it is. Even though, weirdly, we know that there exist circuits, or formulas, there exist truth tables that need like 100 billion gates. So this actually illustrates some of the challenges in theoretical computer science. We're really still at the beginning of the field. There's a lot of things that we don't understand and we cannot prove. Okay. See you on next Tuesday when there will be a quiz.